Okay, thank you, Alex, for the introduction, and also organizers for inviting me. This is my second time in 5 years, and it's great to see this much focused audience. Okay, so this is a title from the organizer, and my real title is, okay. My real title is this. Okay, so I would like to talk about solving higher order inverse scattering problem to see deep inside biological tissue. Okay, so as we all know, the optical imaging is very powerful because it provides us with subcellular resolution, molecular contrast, and non-invasive. But it's very susceptible to multiple scattering noise. And because of that, its imaging depth is extremely shallow. So even small perturbation by the presence of scattering medium can completely spoil the image. So then let me briefly discuss the effect of multiple scattering in imaging. So as you all know, the imaging is an action of measuring the momentum change induced by the target object. So suppose we send a wave with a specific incidence angle, then a tiny fraction of the wave can travel straight through, which we call ballistic wave. And this wave is now deflected by target object, and another tiny fraction will travel straight through. And this ballistic wave will give us the object information. But unfortunately, its intensity decreases exponentially with depth at the length scale of 100 micron in the case of biological tissue. And the rest is all converted to multiple scattering and obscure the ballistic wave. And this is the origin why we cannot see deep inside. If you would like to better, then you should be able to make use of this multiple scattering. But in order to do that, you should be able to trace the trajectory of all these pathways. Okay. If not, then what happens is, even if you send an angle with theta in, the actual angle that hit the target is different. The measured output angle is different from the actual deflected angle, and that's why you cannot actually recover the object, right? So this is the main source of the problem. So in any case, we have to be able to trace this trajectory, and that's what we call higher order inverse scattering problem. So each scattering event is add an order, okay? Suppose there is a 10 times of scattering event, then you have to solve 10 order of scattering problem, okay? But in general, this problem is highly underdetermined, and it's extremely difficult to solve, right? So then how can we approach this problem? So probably the ideal solution is to find the refractive index at each voxel of the scattering medium. But considering that you focus light to a depth of 1 millimeter, then your illumination size will be huge on the surface, right? So then the number of voxels that you need to find out is, huge number. So it's almost impossible to find. So then what will be a practical approach, okay? So in our case, we focus on finding a specific section of the object at a certain depth, okay? Then now you can classify signal into two types. So one type is the wave that hit the target and come back, okay? So this is what we call signal. But then on the other hand, there are also signals that travel at other depths, okay? And those will serve as a noise, okay? Then how can we describe this signal wave? That can be described by this equation, okay? So this is our master equation. So now here, E in is the amplitude of incidence wave with the wave vector K in, and Ti means the amplitude transfer function. For the wave with the K in incidence, the amplitude of the wave that hit the target with the wave vector of K. That's what this Ti stands for. And then now, what's the role of the object, okay? So I mentioned that we are going to deal with the thin object, thin section of object, which will be determined by the objective lens focus eventually. So if the object is thin, then it has a special property, right? If you have a thin diffraction grating, you shine the laser and you have a diffraction. Now if you change illumination angle, then the spectrum is rotating, okay? So thin object has this special property of the shifting of the spectrum. When I indicate tilde, that means the spectrum, okay? So what happens is it receive K in and it produce K prime, but then it has this shifting property. And then, of course, on the way back, you also have this transfer matrix, okay? And then those that doesn't hit the target is described by this, okay? So our task is to measure this and then to find these. You have to factorize them, okay? So that's what you have to do. Then maybe we can have a simple analysis. So suppose we send and measure the n numbers of orthogonal mode, then probably we can have an n square measurement, roughly, okay? But then how many unknowns do we have? So Ti has a n square unknowns, and this has a n unknown. So essentially underdetermined, right? And then furthermore, we have this noise, okay? So this is still difficult to solve, right? So that's where we are, okay? So another way of looking at this problem, now you can represent this in a matrix form. So the combination of this measurement for K in and K out can constitute a matrix R, which we call reflection matrix. Matthias gave us a very exquisite explanation for that. And that can be described by these three matrices, okay? T, O, and T dagger, okay? And R background. So if you are able to find T, then what you can do is maybe you can apply the inverse of T to R, like this. Then maybe that will give us approximately the object information, okay? So that's ultimately what we are going to do. So finding T and applying the inverse is more like canceling the scattering medium, okay? So that is the dream of the people working in this field, okay? So now we made a long journey, maybe about 10 years of solving this problem. We made the first recording of the time-gated reflection matrix more than 10 years ago. And then we solve aberration problem. And then we go ahead and solve scattering problem. And finally, we solve the multiple scattering problem. So I'm going to introduce each by each. Okay. So recording a reflection matrix. So inspired by ultrasound and microwave work. In fact, Matthias, I didn't look at ultrasound paper. I read microwave paper in 2007 in Pierrat. That inspired me, and by looking at that, I decided so we should measure it in optics, and there will be some good way to go. Okay, so that's the beginning of our part of story. Okay, so in any case, in order to solve inverse problem, so the idea is like a maximalist. You should gather all the possible information, right? Even if you do that, you are still deficient, right? In any case, that's the idea. So the reflection matrix, as Matthias has already explained, the concept is you prepare a number of source channels and you send it one channel by another, and you measure the backscattering signal for all the possible channels. The channel could be either position of illumination or angle of illumination. They are equivalent. Or you can tune the wavelengths and you can measure at different wavelengths, which is also equivalent to the time-gated detection. You can also do the polarization gating. So whatever degree of freedom you should use, but unfortunately, this is most that we have. Okay, so now with the reflection matrix, so let me show this diagram. So this is maybe our third generation of measuring reflection matrix system. So the backbone is a confocal reflectance microscope, but instead of a pinhole, because we need to measure all the possible detection channel, we put a camera, introduce a reference wave, and we measure the phase and amplitude of backscattering wave while scanning the focus. So this is the typical result. So while scanning the focus, because there is a scattering medium, the backscattering PSF point spread function look like this. You have an amplitude and phase. Okay. If there were no scattering medium, this has to be a focus. But now you have a spread, but this spread contains the information. Okay. So once you have this, then you can also synthesize this information to send a plane wave. By synthesizing focus wave, you simulate, right? You can send any arbitrary angular illumination. So you can convert this focus-based data to angular-based data, okay? But it turned out that it can have, people have a different opinion, but I think plane wave is a good basis to work with. So I will talk about the reason why. Okay, so now I'm going to talk about a way to correct the aberration. Okay. Okay, so going back to the master equation, as I mentioned, this is extremely difficult to solve. So what we can do first is we make an approximation, right? So we make an approximation to be a delta function, meaning that we will ignore the wave that is deflected and we will only trace the ballistic component, but we will find its phase retardation, okay? Then the components that deflected and having different k from k in can be put in the noise factor, okay? And likewise, we also model think the returning path as a delta function. Then the problem is reduced like this, okay? So the recorded wave is phase retardation and change of the momentum and another phase retardation. And then we have a bunch of the multiple scattering noise, okay? So the question is, out of the round trip measurement, how are you going to separate the input aberration and output aberration, okay? So this hasn't been solved up to this point. In order to solve this, people introduced the concept of guide star. When you have a guide star, then you can ignore the distortion on the way in, essentially converting the problem as a one-way problem, okay? But now we are going to solve this two-way problem as it is. Then the problem look much better than the original because we have an n square measurement and here we have only 2n unknown, okay? So if there were no noise, then you don't need many measurements, right, to solve that. But if you would like to see deep and then you will have many deflected components, then you need overdeterminedness, okay, to cope with multiple scattering noise. So now I'm going to talk about a way to find theta in, the aberration in and aberration out separately. So, so this movie shows the case without aberration. Okay, so this is an illumination wavefront, and this is a measured wave. And then now here I'm showing you the spectrum. Okay, so the spectrum is rotated as you change the illumination angle, as I mentioned. But then now if you look at the spectrum in a delta K space, if you compensate for the illumination angle, and if you are looking at spectrum in a rotating frame, yes, let me show that again. Anyway, so the spectrum is stationary and it's identical irrespective of the illumination. But then when we introduce aberration, then the image is distorted and you have a rotating spectrum. And if you look at the spectrum, they are not identical from one angle illumination to another. Okay, so that is a consequence of aberration. And when there exists multiple scattering, then it's even worse, right? So spectrum is masked by the scattering noise. So then now we know what is supposed to be, right? If there were no aberration, then the spectrum should be identical. Okay, so the idea of correcting or finding the aberration is to truncate this in a way to maximize the similarity of the spectrum in the rotating frame. Okay, so that is the conceptual idea. But then let me give a brief mathematical expression. So we construct a reflection matrix in a spatial frequency domain. So each element is k in and k out. And then now let's take a look at two columns, two representative columns. So two columns means each spectrum. So the spectrum has this form, okay? But instead of playing in this original basis, we go to the delta K space. So we compensate the amount of shift. Then this become OK out, and measuring the spectrum at another angle, the object spectrum become the OK, in the delta K space. So in a way, we make the object spectrum invariant by playing with the spectrum in the delta K space. And then, of course, you have incident aberration and outgoing aberration. So then let's simplify the problem. If there were no output aberration, then if you compare these two, and if you compute the correlation, then that will immediately give you the input aberration. Okay, so that is the case if there were no output aberration. But the presence of output aberration give additional phase, and it will give rise to an error. Okay, and then you also have a multiple scattering noise that give you another error. So this first estimation give you the approximate input aberration, not the exact aberration, right? So then what you need to do is you now have to deal with the output aberration. So what we do is, instead of comparing two columns, we compare two rows of the matrix. Okay. Then now you have you will find the approximate output aberration. Okay. But then in the first round, you first correct the input aberration, so you reduce the error, and then you go on a correction of the output aberration, and you do the iteration, okay? And then that will gradually converge to a solution. So then this approach is very unique because we don't treat the object as a variable. We are not trying to find the object, right? So object is not a variable at all, which means you reduce the effective number of variables. Okay, this is very critical, especially when you want to solve the inverse problem. Another thing is there is no assumption about the guide star. So no guide star is necessary, and also very robust to scattering noise. So what I mean by this, so I just illustrate here to compare one column to another. But in actual implementation, we compare one column with all the other columns. In a coherent way. So then the SNR of finding this phase scale with n. Okay, so which means even if multiple scattering is n times stronger, you can still find the solution. Okay, so that's the robustness of the algorithm. So as I mentioned, you do this computation. You find the input aberration, and then you go on output side and you correct the output aberration. Okay, so you do this sequentially. So now this shows the way iteration goes. Okay, so input and output and input and output. And then you observe that the object is gradually clarified. This is not a simulation data. This is an experimental data. Okay. But then we realized that this operation is a new kind of matrix decomposition. Okay, so we have a reflection matrix, but at the end of the day, we factorize this into three components, right? So this. Okay, so matrix is decomposed into two diagonal matrix and one top-list matrix. Okay, so that's what our operation does. So eigenvalue decomposition, you have a power iteration or iterative time reversal, iterative way of decomposing a matrix. So we introduce a new kind of iterative way of decomposing matrix in a new kind of form, which is relevant to imaging a sample. And then, of course, it excludes multiple scattering noise. And then from each component, you can find the aberration and object. Okay. So with this, we first test this with in imaging zebrafish. So we have a volumetric image. So in order to have a volumetric image, you have to record reflection matrix at each depth. Okay, and then you operate the algorithm we call class algorithm. So this is from surface, and you go deeper and deeper. This is reflectance imaging, which means label-free imaging. The structures you are looking at here is myelinated axon. So the lipid in biological tissue give rise to Moore scattering. So you are looking at that, okay? So this is a comparison. By the way, this is 21 day after fertilization from zebrafish standard. This is pretty old one, okay? So then this is a typical confocal fluorescence and confocal reflectance. Actually, this is a confocal with time gating, and this is class image. You can see a lot more fine structures, right? Hmm? This we only corrected. Corrected the pupil aberration. Yeah. So we didn't get to that point yet at this time. Okay. Yeah. Probably we analyzed this area by area. Yeah. Okay. So then now after solving this, we move on to the scattering problem. In fact, our interest was through skull imaging. So through skull imaging, you have a fresh tissue covered by a skull. Then maybe skull is the major factor of the distortion, right? So maybe you can consider this as approximately as a scattering plate located at a certain distance from the object, okay? And then we realize, and also people already know that the angular basis is not a good basis, okay? You send an angle, then this scattering plate will change the angle. So you have to find the angle and the phase of that particular angle, which is difficult to find. And also the problem exists on the way back as well, okay? So then now, in order to solve this problem, it will be better to change the basis, okay? So in physics, you need to be careful, and if you are smart enough to choose the right basis, then you can kind of diagonalize the problem, right? So that is also applies to here. So instead of using plane wave as a basis, we consider the focusing wave on the skull as a basis, okay? Then the effect of skull is giving rise, it will give rise to the phase retardation of this focused wave, okay? And then the reflected wave by the object, you can consider it as a superposition of the focusing wave back to the skull, okay? So that's the basis. And then now, the effect of skull is again changing the phase of the focused wave. So in this way, we change scattering problem as a phase retardation problem, okay? So the process is following. We have an original matrix which is focused on the object plane. So this is original matrix, but you computationally change your basis because we have a phase and amplitude. You can always change the basis so that now your illumination is on the skull and your detection is also skull, okay? So the way to do that is from original matrix, you just multiply the free space propagation matrix. Then you are all set. So then this new matrix in a W coordinate can be written in this form. But in order to write in this form, you need an approximation, Fresnel approximation. Then, as I mentioned, the effect of skull is a phase retardation in and out. And the object spectrum is not the real object spectrum. It's an object spectrum with a quadratic component. But important point here is by changing the basis, now the equation is formally equivalent to the previous aberration problem. So you can apply the same algorithm, okay? So, and then we realized the in vivo through skull imaging. For this purpose, we choose 1.3 micron as an excitation source. So this is a volumetric image. Here is a skull, which is measured by second harmonic generation. And we could go as deep as 650 micrometer from the bottom surface of the skull. Okay, so these are the sectioned image. This is an OCM image, and this is our image. You can see the myelinated axons pretty clearly. Okay, and these are the aberration of the skull. In fact, can you see the dots here? That's a real structure. That's a real osteocyte cells. And then, of course, we could obtain the resolution that is comparable to the diffraction limit. So in the context of the label-free imaging, and this is the first through-skull imaging, and also with the resolution very close to the diffraction limit, and also this is the deepest depth you could reach with the label-free imaging. We did longitudinal imaging. So for the same mouse, after 26 days postnatal and 33 and 47, we keep observing the same area under the skull, and you could observe the enrichment of the myelinated axons. Okay. So in fact, this can lead to study the myelin-associated neurological disorder, such as multiple sclerosis and Alzheimer's disease. Of course, you can observe the elongation and also thickening of the myelin under the skull. Okay. So this is yeah.
Is there any scattering in your corrects the brain, the skull, sorry?
Right.
And behind the skull there is some scattering. Are you compensating for this scattering, or is it negligible compared to the skull?
Scattering from fresh tissue. Yeah. I think it exists. But we mainly, by choosing this skull plane, we mainly ignore them, meaning we mainly treat them as a noise. Okay. Yeah.
You don't try to compensate for it?
Yeah, I think for through-skull imaging, probably you can gain something, but it's not a major factor. But also, frankly speaking, it's also more difficult to correct. Yeah.
So what is the scattering frequency?
Of the skull? Brain tissue, I think it's maybe similar, 100 micron. Yeah, around that ballpark. Yeah. Maybe for 1.3 micron, maybe 150 micron or 200 micron. Yeah. Okay, so now I'm going to talk about the multiple scattering. So the scattering medium will give rise to this, multiple bendings. Okay, so then maybe in order to, trace this, one way is to find multiple phase plate that produce similar light trajectory as the original scattering medium. Okay, so then if you are able to find them, then you can claim that you could solve higher order inverse scattering problem. So now this is a reflection, right? So you have a phase plate on the way in and also on the way out. So if I unfold it, then this is a transmission path and this is a reflection path. And each phase plate can be described by a transmission matrix of each layer. Then reflection matrix can be described as follows, right? So then from here, you need to find each, okay? But then solving this is now straightforward because I already explained how to find a single phase plate, okay? So now if you have a multiple phase plate, then you change your basis to a certain distance and then you find it and you go to another and you find it. And you do this iteratively and then you can gradually find multiple phase plate like that, okay? But then, as I mentioned, the previous conjugate approach, we use Fresnel approximation. But then when you use Fresnel approximation, you cannot find phase plate close to the object. Okay, so you have to get rid of that approximation. So we develop a similar kind of finding the phase plate, okay, without resorting to the Fresnel approximation. So now to simplify the problem, let's imagine that we have only one phase plate and object, and we don't have all the other phase plate, okay? So now we shine the focus at one point, and then we measure the signal reflected by the object, okay? So your illumination is this phase plate and your detection is object. Then maybe you can have this kind of phase map. So you have this spherical wavefront, which is due to the illumination, and you have object information. And now you can also shine the focus at the other point, and you have this image. And then before comparing them, we get rid of the spherical components because we know what the spherical component will be, okay? And then you are left with the object information. But then if you compare them, then you can get a relative phase. And their relative phase is the relative phase between rho 1 and rho 2 at the plate G3, okay? So this, logic is exactly the same as the original class algorithm, but now you can work at different bases, okay? So you can find the relative phase, but again, due to the presence of all the other phase plate and noise, this first estimation is not correct. It has a noise. So in order to solve that, you have to again go on an iteration to, different layers and also layers in the output path. So now I'm going to show you some result. So we fabricated an artificial layer, in this case 3 layer, okay? And then we put a resolution target underneath, okay? And then we apply this multi-conjugate algorithm. So this is a result when you apply a single layer algorithm. And this is the original confocal, usual confocal image. So single layer reconstruction in terms of imaging is already good, but the phase plate look like this. But now if you apply multi-layer algorithm, then you can separate each layer, okay? So this is, of course, the same as what we designed, okay? So now this is another interesting experiment. So we put an onion. Onion is a good layered structure. So we put an onion, but the thickness of onion is 1 millimeter, okay? And then now we will measure the reflection matrix, and then we apply our algorithm. So this is a typical OCM image of the target. And these are the phase plates that we identified out of the reflection matrix. Now you can see the cell walls and cell nucleus. And this is a phase image. So in reflection, you find the phase map of each layer, okay? And then if you know this, then you can correct this in your measured matrix, and you can have this image, okay? So this is a quite exciting result. And then, of course, we apply this to, in vivo through-skull imaging. So the data is the same, your algorithm is different. But in this case, we deal with the mouse, mature mouse. The thickness of the skull was about 200 micron. And we apply our algorithm to identify the face plate. You see the blue dots here. The blue dots are actually the cell body of the osteocyte. So by doing so, you can actually find the structure of the scattering medium using this algorithm. And then, of course, you can recover the myelinated axons. So here, I show the 5 phase plate, which means we solve the 11 orders of inverse scattering problem. 5 on the way in, 1 object, and another 5 on the way out, okay? Yeah. Yeah. Yeah, that's a good question. So initially we use a single plate, and we try to move it, and we see the improvement. In doing so, we find the range where, and then we gradually add one after another. Yeah. Yeah, I think this layer is just an optical representation of the real scattering medium, right? So it doesn't need to be exactly, or precisely to be a certain depth, right? Yeah. But when you choose a certain depth, then the meaning of this phase is a projection of the structures nearby. Okay, so it will still report the microscopic structure around the face plate. Okay, so I think the difficult part is almost done. So now I'm going to talk about some other application. So once you solve this problem, then you can find essentially the transmission property of the scattering medium. Okay, and then you can find what kind of wave you should send to actually generate a focus inside the scattering medium. So this is one kind of example, right? So out of that, you find it, and then you use SLM to counteract that, okay? So you shape the illumination to counteract this. Then actually when wave goes in and this distorted wave converted into sharp focus. And then on the way back, if it hit the SLM again, then it will recover a sharp focus. So this is initial PSF, but when you do this, then you recover a sharp focus like that. Then you don't need any computation at this point, right? So this is without SLM correction, and this is with SLM correction. So essentially, you cancel the scattering medium, okay? So this opens the possibility of applying this to multiphoton imaging, which requires the physical focusing. So with our measurement, we find the aberration map. But one thing interesting here, so we have a myelinated axons, but those areas that doesn't have myelinated axons, you can still find an aberration because the tissue structure there will generate the scattering, the thin section from the tissue. So even if there is no visible structure, you can still find an aberration. And then we can correct the aberration at area associated with that section, okay? So then this is a multiphoton imaging and before and after correction. And of course, you can also propagate the correction to a different depths, and you can have a multi-depth imaging like that, okay? We also apply this to super resolution imaging, the single molecule localization microscope. So on the one hand, we have a class microscope, which find the sample-induced aberration, and we pass the information to SRM in the emission beam path of the single molecule localization microscope. This is the deep tissue imaging demonstration. Okay, so what is the direction? So far, actually, what we measured is our reflection matrix initially measured time-resolved measurement, which means that we recorded multiple scattering with a small deflection angle because our time gating is tuned to the target depth, right? So within time gating window, we recorded reflection matrix. The idea is, of course, you would like to reject multiple scattering as much as you can. But now you would like to claim more multiple scattering. So in order to do that, probably you need to loosen your time gating and accept more multiple scattering, and then try to trace them. So that's probably our next direction. So far, we could claim 600 times of ballistic wave with our algorithm, which means maybe 3 mean scattering mean prepass deeper. Yeah, after all these work, you go 10 to 13, okay? So now you want to go further, then you have to claim more. So we are in a logarithmic curve, okay? That's an unfortunate fact. Maybe if time allows, then I will briefly talk about our recent work about the transmission matrix of nonlinear scattering medium, okay? Which is not totally true. So we considered a collection of barium titanate which generate second harmonic signals, okay? Then, in the case of linear scattering medium, the transmission matrix, faithfully describe that. So in this case, how can we describe the second harmonic scattering medium, okay? So now imagine you turn on one channel and then you measure SHG. And then now you turn on another, you have another spectral pattern of SHG. But what if you turn on both J and K? You have this, right? But then if you subtract these two from this, if it were linear, then this is supposed to be 0, but it's not the case, right? Because this is nonlinear, okay? So the way to explain is like this. If you turn on one channel, then the signal at a certain detection pixel can be described like that. So the square of the incident wave, TLJ describe the transfer function from J's channel to L's particle, and then you have a susceptibility, and from L to alpha you have another transfer function. But now if you turn on two channels, then it has to be described in this way. Then you have a square term and you also have a cross term, okay? So in order to properly describe the second harmonic scattering medium, you need to find these components, all three components. Okay, so now this can be described by this form. This form itself is very familiar, but usually previously this alpha jk is a polarization state, but here we have a spatial state. So now if you look at the phase of cross term, when you change the phase of J's channel, the phase change is twice the phase that you impose, but the cross term is linear like that. Okay. So in any case, to properly describe this nonlinear scattering medium, you should measure these components, which is element of the scattering tensor of rank 3. And in order to measure that, if it were linear medium, then probably you turn on each channel and then you measure it, then you are all set. But for second harmonic, you have to turn on two possible pairs. And then from these two possible pairs, you need to find the cross term for these two channels. So for example, if you are considering 49 channels, the linear medium you need only 49 measurement, but second harmonic you need this many measurement. Okay, so these are experimentally measured tensor, and then maybe J and K is a little cumbersome to think, so we squeeze this J comma K to index P. Then this look more like a matrix multiplication. So this is like a squeezed tensor, and S is a quadratic component, which is an outer product of the input wave. Okay. So in linear medium, you can, from the transmitted spectral field, you can find an input by means of the inverse of the matrix. And you can do something similar. So you project a flower pattern, then you have a speckle, SHG speckle. But if you have measured the tensor, then maybe you can multiply the inverse of this squeezed tensor to measure the SHG. Then that will give you this S, which is an outer product of the incident wave. And then you can solve this equation, then you can recover the original. So this is a way to solve the inverse of the tensor. Okay. Maybe I'm not sure about the good news of this characterization. Maybe this is more complex than linear, so maybe it can be more difficult to decode when you play with or you are playing in the cryptography. Or maybe you can use this in optical computation, because second harmonic generation, put your input into a high dimensional space. Maybe you can use this as a kernel operation. So that could be some possibility. Another thing that you can learn here is that unlike the linear scattering medium, you cannot do the wavefront shaping. You cannot generate an arbitrary SHG wave. Of course, simply speaking, the number of output channel is much larger than the input channel, right? So that's one reason. Another way of interpretation, if you would like to generate a certain pattern, you will find the S, but that doesn't guarantee that you find the input solution or the solution of this square equation. Okay, so this is the end. In the end, I think we have a similar or same philosophy as Alex. So we measured reflection matrix, and then we solve inverse problem in a different framework, I believe. And with that, we could make use of the multiple scattering. We convert multiple scattering into signal, and we could go deeper than before. We are trying to expand this to solve a real biological problem. And also, like Matthias come from ultrasound to optics, maybe our approach can go to ultrasound on the other way around. Okay, yeah. So my group members, yeah, and collaborators, and yeah, thank you for your attention. Yeah.